Walk into a casino. Every game is a random experiment. The roulette wheel spins, red or black, odd or even. The slot machine pulls cherry var 7. Each game has a set of outcomes and a probability for each. The house knows the math. The house always wins in the long run. Probability theory is the math, and it runs every statistical method in biology, from p-values to Bayesian inference to population pharmacokinetics. The sample space is the set of all possible outcomes. Flip a coin, heads or tails. Roll a die, 1 through 6. Sequence a gene at C, G or T at each position. Measure a drug concentration, any non-negative real number. An event is a subset of the sample space. Rolling an even number, the set 2, 4, 6. The probability of an event is between 0 and 1. The probabilities of all possible outcomes sum to 1. These axioms, Kolmogorov's axioms, are the foundation of everything. A random variable maps outcomes to numbers. Flip a coin, x equals 1 for heads, 0 for tails. That's a discrete random variable. Measure drug concentration in blood. X can be any positive real number. That's continuous. For discrete variables, the probability mass function gives p of x equals x for each value. For continuous variables, the probability density function gives the height of the curve. Probabilities come from integrating the area. The distribution of a random variable tells you the complete probability structure of the experiment. The expected value is the long-run average. Play the game 1,000,000 times and average the payouts. E of x equals the sum of each value times its probability. A fair die, E of x equals 1 6 times 1 plus 1 6 times 2 plus all the way to 6. That's 3.5. You'll never roll 3.5, but it's the average. A bias coin with 70% heads, E of x equals 0.7. In population pharmacokinetics, the typical clearance, statistical, is the expected value of clearance across the population. It's the average factory speed. Expected value tells you the center. Variance tells you the spread. Per of x equals the expected value of x minus mu squared. How far outcomes deviate from the average, on average. Standard deviation is the square root of variance, same units as x in popPK. The inter-individual variability omega squared is the variance of the random effects. An omega squared of 0.48 means clearance varies with a standard deviation of about 69%. That's the spread around the typical value. Coefficient of variation, K-phi%, equals standard deviation divided by the mean times 100. Each casino game has its own distribution. The Bernoulli, 1 trial, success or failure. The coin flip. The binomial, an independent Bernoulli trials. How many responders in 20 patients? Poisson, counting rare events in a fixed window. Mutations per gene, reads per region in RNA-seq. The normal, the bell curve. Continuous, symmetric, defined by mean and variance. Appears everywhere thanks to the central limit theorem. The log normal, take the log, and it's normal. Clearance in popPK is log normally distributed. That's why we model CL equals theta times exponential of eta. Random variables assign numbers to outcomes. Expected value is the long-run average. Variance measures the spread. Distributions describe the full probability structure. Bernoulli, binomial, Poisson, normal, log normal, each models a different type of randomness. Next, what happens when you learn new information?